Fumeng, Northwestern University. So, since this is not a best paper presentation, I'm more relaxed right now. So this work was done a while ago, but I still think the results are very interesting, and also I'm very grateful for the support by my co-authors, James Tompkin, Nick Harrison, and David Laidlaw. A little from other presentations, I will start with 1 minute summary. So visual cue in this paper means shading, shadow, etc., and the classification accuracy estimation task represents multi-class perception. And the immersive scatterplots means 3D scatterplots in a VR head-mount display, and the effects we found were generally small, except for one visual cue. Though this 15-page paper in one sentence, the effects of shading, etc. on multi-class perception in VR are generally small, except for one visual cue. And in the next 8 minutes, we will go through our experiment and results together to identify that visual cue. So there are many visual cues available for VR applications, such as shading and shadow. According to perceptual psychology literature, they and their interplays between them can have strong but complex effects on our perception. The examples here show how shading and texture affect our perception of shape. However, perceptual psychology often focuses on a handful of real elements, like two spheres or sometimes just one. For visualizations, we may have hundreds or even thousands of real elements where previous findings may not be applicable. Additionally, lots of perceptual psychology experiments use abstract low-level tasks, such as comparing two values. For us, we really want a realist task to support visual analytics in the real world. Therefore, we derive a task from Kang and his colleagues' paper, which I really like. We ask participants to estimate classification accuracy from a neural network's last hidden layer output. So, we start with training neural network and save the instance after each epoch. We input the test dataset and extract last hidden layer output. We then apply dimension reduction technique and render the dimensional reduced output as scatterplots in VR and on the desktop. So I will show you example of how last hidden layer output changes with classification accuracy. As we train the network, the classification accuracy increases, and the clusters in last hidden layer output became more and more salient. Classification accuracy reflects neural network's performance. Their task is essentially a multi-class perceptual judgment. It happens when the model designer tries to identify misclassified instances to improve or debug a model. For the experiment, we manipulate 6 different variables to add coverage as much design space as possible, including 4 visual cues, which may display strong effects according to perceptual psychology literature. And I will introduce them one by one. First, we consider different devices. We have desktop plus monitor as a baseline, and we also have a VR head-mount display for our purpose to support VR applications. The first visual cue we consider is visual motion. We have both static and dynamic conditions. Excuse me. In static conditions, participants see a fixed graph. In dynamic conditions, participants can interact with the scatterplot. And I will show you demos of how participants interact with the scatterplot. On the desktop, they can rotate the scatterplot around its center using the mouse. They can also navigate the scene using the keyboard. And in VR, besides that the participants can rotate the scatterplot using the VR controller, they can also walk in the room to see the scatterplot from different perspectives. The next visual cue we consider is shading. We have flat shading, simple shading, and ambient cooling. All are common choices, and each gradually adds more visual properties to the scatterplot. The third visual cue we consider is graphic projection. We have both orthographic and perspective projections. The difference is that in perspective projection, for the spheres are smaller, size is used as a depth cue. The last visual cue we consider is dimensionality. We project a high-dimensional output to a 2D space or a 3D space. Note that the top and bottom in the same column are the projections of the same dataset. And finally, we consider different data models. They mean different cluster shapes and different numbers of data points. First, we have a text dataset trained on a memory neural network to generate 1,000 spheres and 6 different classes. Also, we have an image dataset trained on a residual network to generate 5,000 spheres and 10 different classes. For the experiment design, we have 6 different variables, which generate 52 experimental conditions. We assign 26 conditions to each participant, and in each condition, they repeat 4 trials. Each trial is capped at 1 minute. And we recruit 32 participants who had prior experience with machine learning from Brown University. For our quantitative analysis, we record 2 measures. First, we have error magnitude, which is defined as the difference between participants' estimation and the actual classification accuracy. Second, we also have response time, which is defined as the time between a scatterplot was first shown and then removed. To estimate the effects, we use Bayesian multi-level modeling. I put up some equations here to basically fill in the space. You don't have to read them. To guide our results reporting, we ask 3 different guiding questions. First, since we have 6 different variables, we are curious about how does each variable affect participants' performance. We extract the posteriors of the fixed effect and then plot the posterior distributions. There are many interesting observations, such as this null effect. However, I want to indicate that visual motion can decrease error magnitude, but also increase response time. And next, since we have 6 variables, we want to know the interaction effects between them. Again, we plot the posterior distributions of all 2-way interaction effects. There are many interesting observations. I want to point out one example. This is an interaction between device and shading. It means that different shading levels affect response time differently depending on the device being used. And lastly, we look at all 52 conditions. We use the medians to plot this figure, and the whole loss means uncertainty range. This figure visually summarizes all the effects. For example, for the same image dataset and static conditions, adding shading slightly decreases error magnitude. However, for the same image dataset and dynamic conditions in VR, adding shading slightly increases error magnitude. For response time, adding shading consistently increases in response time. To summarize and conclude this work, we navigate the complexity of assessing the effects of multiple visual cues for real-world analytics. We conduct an experiment for 2 different datasets on 2 different devices. We found that the visual cues generally have small effects, but the visual motion can largely reduce error magnitude but also increase response time. For future work, we suggest that they could use simple shading, but focus on designing effective interactions and animations to leverage visual motion. Thank you so much for listening.